Let's talk about some soil factors that are going to influence how the microbial environment in that earth environment is put together. So when we talk about some of those factors, there's a couple ways we can think about this, and it's really thinking about what we call the three-phase soil system. So there's going to be solid or mineral and organic phases. So there's going to be components that are solid and organic. There's going to be liquid components, so there's going to be ability for water to move, predominantly water to move through the soil, so that's the liquid or solution phase. And then, believe it or not, there's actually a lot of availability for gases to move in between soil particles, so that's what we call the gas phase or the atmosphere, the soil atmosphere. So we're going to cover each of these three things high level in this pre-lecture, and then in class we're going to talk about how they apply to us as environmental engineers. So first, I just want to talk about the solid phase. So in general, when it comes to soil or to mineral particles, they're classified by their size. So on the right side of your screen, you're going to see a different type of particle, sand, silt, or clay, and the different sizes associated with those. So we call those mineral particles. And they have different distributions. So you can kind of see some of these distributions down below, the number of pores and whether things are fine or coarse. So the texture and what type of solid the soil is going to be made up of is going to influence surface area in the system and what kind of pore spaces are going to exist. So in general, most of our materials are silicon and oxygen that are found as the most abundant elements in Earth's crust. And they interact with lots of other elements to make minerals. So for example, silicon dioxide is quartz. Mica has that long structure that you see there. And in general, when we look at the composition of soil, a lot of it's going to be mineral, about 45%, about half of it's going to be pore space, and then the remainder is going to be organic matter of about up to 5%. So the different types of particles that we have can influence not only surface area, but what types of organisms could be there. And in general, when it comes to soil architecture, normally we have individual particles forming aggregates. So the particles themselves clump together and they form secondary structures that we sometimes hear called PEDs. And basically what will happen is microbial components will get together and they will form polysaccharide layers and potentially other metabolites. And this will form kind of a glue that brings soil structures together. And we can have fungal hyphae or root structures also providing structure. So the microorganisms themselves are really good at providing kind of this aggregation of particles that you see to the right on the screen. But then not only do we have the aggregates, but we have the spaces in between the aggregates, and we call this pore space. It's the voids where the air can move between particles or where water could move between particles. So we have intra-aggregate pores, which are between aggregates, and inter-aggregate pores, which are between particles within an aggregate. And what those different types of aggregates are going to allow us to do and what those different pore sizes are going to do is allow for preferential flow of water. All microorganisms are going to need water to survive because we live on Earth. So having enough moisture is going to be critical, and the soil structure normally allows for that moisture to flow. The other thing that I want to mention, kind of related to soils and solids, is what we call soil profiles or horizons. And these different soils have different physical and chemical properties. So what you'll see on the right is these different labels for soil horizons, where you have what's called, so for instance, the O horizon, which is mainly organic matter. And then below it, something that we call the A horizon, the surface horizon, and then moving down, each of these different levels are going to have different physical and chemical properties. So if you get all the way down to the R horizon, you're going to see bedrock. So basically, this is a way for us to describe things. And you can see on the left side of the screen one example of a soil profile, and then here's a slightly different one. So you can see the O, the A, the E, all the different horizons, but they're in different places. So here's another example where we have lots of different things going on. Oops, went too far forward on the soils, but you could see the different profiles that we can have. One other thing that I want to make sure we talk about when we talk about solid components of our soil is something called cation exchange capacity. So basically when we have clay particles, there are negative particles or negative charges associated with those clay particles, and clay itself exists as a lattice of inorganics. So it's very easy to substitute what we call divalent or trivalent cations within those different clay particles. And we can also have lots of hydroxyl groups, which are going to encourage ionization. So basically what will happen is if you look over at the right side of the screen in the top right, you're going to see lots of ions are going to be moving in the system. So the clay particles themselves have the negative charge, but as a result, they can have lots of cations near them in order to neutralize that charge. And then when we talk about solids, solids in soil can be colloids based on their size, and they have a small size but a large surface area. So there's going to be lots of cationic sites on the outside of a soil particle, particularly one that's made out of clay. And so those open sites are going to really help with reactions and moving those cations around in the system. And cation exchange is going to depend on not only the concentration of the cation in soil, but also absorption affinity as well. And absorption affinity is basically a function of charge density and the size of the ion. So basically what it tells us is our preference for having those cations in the soil. So for example, it's more preferential, let me grab my laser pointer, it's preferential to have aluminum because it has a +3 charge. That's more preferential than calcium, but calcium and magnesium have about the same affinity, but their affinity is greater than potassium's affinity. So it's based not only on the charge, but the charge density of specific cations. Then another thing that's going to be important as we kind of transition from the solid phase into the liquid phase is the soil pH. And the key thing with soil pH is that it's going to affect the solubility of chemicals in soil. So if we're doing something like bioremediation, pH is going to be really important because it's affecting solubility. And it's also going to impact the degree of ionization of compounds in charge. So that's going to be very important. So on the left side of the screen, we have the traditional definition of pH. And in general, when we say acidic soils, we're looking at soils with less than 5.5 pH. Neutral soils are in the range of 6 to 8. And alkaline or basic soils are greater than 8.5. We tend to see the word alkaline more than we see base. All right, so that's going to cover a lot of our solids. Let's talk very quickly about the liquid phase, and sometimes this is called the soil solution. So in general, microorganisms are approximately 70% water. This means that the composition of the liquid phase in soils is extremely critical for biological activity, and that solution chemistry, it's basically aqueous chemistry that's happening in solution, is ultimately going to control how much microbial or plant growth we have in a specific soil. So a couple of factors that are going to influence soil chemistry. Water movements are going to be huge. So rainfall events, irrigation is particularly important in Nebraska. These are important because they contribute to mineral weathering. So remember that changes what's in the soil. And that we're also going to see organic matter formation and decomposition as a result of having enough moisture. So that's going to change mineral and organic components. We can also have anthropogenic activities, so irrigation, fertilizer use, pesticide addition, chemical spills, all of that's going to affect chemistry. And the reason we care so much about the chemistry is because it affects what's called bioavailability of nutrients, whether or not those nutrients are actually available and can be uptaken, I don't know if that's the right word, but uptaken by a microorganism in order to do their metabolic activities. So this is just a little figure that you can pause this screen just to take a look at it. It's in your book as well, but it just shows all the different types of reactions that we've just discussed that are going to influence that soil chemistry. So there's things like the roots, there's precipitation from solution, there's cation exchange, there's microorganisms, and all these components are going to have an impact on what's going on from a chemistry standpoint. And then this table here is going to actually help you answer one of your pre-lecture questions. And so what this table has is a bunch of different cations on the left side. And then based on whether we have an acidic soil, we can see that, for example, for sodium in an acidic soil is generally present in the form of Na+, but in an alkaline soil, normally we find sodium in different forms. So we find it sometimes as a sodium sulfate, sometimes a sodium carbonate. So when we're at different pHs, we can have different forms of specific cations present, and that's going to be really important chemistry-wise. Last couple things that we'll talk about. One of the big ones is pore space. So pore space is really, really important for water availability. The ideal conditions that we have is where water is easily available, but we don't have a saturated situation. So when we have our solid phase, this is just bedrock and things like that over here. But when we have pore space and we have all these little spaces in between, if we have very small soil moisture potential down here, this is where plants are going to wilt. They're not going to grow really well because there's not enough moisture around these aggregates for them to grow. But as we start to reach what we call field capacity, there's more water available for plants and for microorganisms to be able to do what they need to do. When we hit saturation, we're having water normally come out of the soil, or it's moving, and this isn't necessarily ideal either, because this is going to cause that solid kind of matrix of things to shift a lot more, and that's not super stable for microorganisms or for plants. So being too saturated is actually not a good thing. Last thing we'll talk about really quickly is the soil atmosphere. So there are pore spaces in the soil itself, and they need gases from the atmosphere. They need the oxygen, right, if they're aerobic. So a lot of times when we think about what's in the actual soil, what you can see here is this is what's atmospheric nitrogen, this is atmospheric oxygen, and this is in a well-aerated soil. That's going to be about the same as the atmosphere. But if we have something that's saturated or fine clay, we normally start to see a loss of oxygen and a little bit of an increase in nitrogen. So depending on where we are, the gases that are going to be able to dissolve in and out of solution is actually going to have an impact. Because the soil and the atmosphere are in contact, they have the same basic composition, but when it starts to change, it's going to have an impact on plant and microbial activity, because the portion of CO2 and O2 are going to be important, especially in soils that are not well aerated. So just naturally occurring soils sometimes aren't well aerated. And then think about your aerobic and your anaerobic organisms, right? Like they have gases that they release and use in order for their metabolic reactions to occur. So they're going to need this pore space where air can actually get in. That's another reason that we don't want things super saturated, because then gases can't diffuse really easily between spaces. So that's going to cover some of the solid components of soil, some of the liquid things, and a little bit about the gases. And what we'll do is we'll take what we've learned about these concepts and we'll start applying them to why it matters to us as environmental engineers when we get into class.